Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the mathematical characteristics of continuum functions. Let's firstly talk about the total differential. Values of two independent intensive properties are sufficient to fix the intensive state of a simple compressible system of specified mass and composition, for instance, temperature and specific volume. All other intensive properties can be determined as functions of the two independent properties, such as P equals P TV, U equals U TV, H equals H TV, and so on. These are all functions of two independent variables of the form z equals z xy, with x and y being the independent variables. It might also be recalled that the differential of every property is exact. The differentials of non-properties such as work and heat are inexact. Let's review briefly some concepts from Cassius about functions of two independent variables and their differentials. The exact differential of a function z continuous in the variables x and y is. This is the fundamental relation for the total differential of a dependent variable in terms of its partial derivatives with respect to independent variables. This relation can easily be extended to include more independent variables. If the coefficients m and n have continuous first partial derivatives, the order in which a second partial derivative of the function z is taken is immaterial. That is, in words, this equation indicates that the mixed second partial derivatives of the function z are equal. The relationship in this equation is both a necessary and sufficient condition for the exactness of a differential expression, and it may therefore be used as a test for exactness. When an expression such as m dx plus n dy does not meet this test, no function z exists whose differential is equal to this expression. In thermodynamics, this equation is not generally used to test exactness, but rather to develop additional property relations. Now, let's talk about the two important relations for partial derivatives, that is, reciprocal expression and cyclic relation. The function z equals z xy can also be expressed as x equals x y z if y and z are taken to be the independent variables. Then the total differential of x becomes. Eliminating dx by combining the two equations of dz and dx results in this expression. The variables y and z are independent of each other and thus can be varied independently. For example, y can be held constant and they can be varied over a range of values. Therefore, for this equation to be valid at all times, the terms in the brackets must equal 0, regardless of the values of y and z. Setting the terms in each bracket equal to 0 gives two important relations. The first is the reciprocity relation. It shows that the inverse of a partial derivative is equal to its reciprocal. The second is the cyclic relation. An equation of state P equals PTV provides a specific example of a function of two independent variables. The partial derivatives m and n are themselves intensive properties because they have unique values at each state. The figure shows that the liquid, vapor, and two phase regions of a PVT surface projected onto the PV and PT planes. In Figure A, several isotherms are sketched. In the single-phase regions, the partial derivative, given the slope is negative at each state along an isotherm, except at the critical point, where the partial derivative vanishes. Since the isotherms are horizontal in the two-phase liquid-vapor region, the partial derivative vanishes. The partial derivative vanishes there as well. For these states, pressure is independent of specific volume and is a function of temperature only. That is, P equals P, T at saturation. Figure B shows the liquid and vapor regions with several isometric superimposed. In the single-phase regions, the isometrics are nearly straight or are slightly curved, and the partial derivatives is positive at each state along the curves. For the two-phase liquid-vapor states corresponding to a specified value of temperature, the pressure is independent of specific volume and is determined by the temperature only. Hence, the slopes of isometrics passing through the two-phase states corresponding to a specified temperature are all equal, being given by the slope of the saturation curve at that temperature, denoted simply as dP over dt. For these two-phase states, we then have this relation. Okay, that's all for this task. Thank you very much, and see you next time.